For a few minutes about Newton's second law, which relates the net force on an object to the resulting acceleration of the object. Except let's restrict the motion, the forces in the motion, to be one-dimensional, that is along a single axis, and we won't consider here the possibility of moving in a plane. Here comes the object we're going to consider, Mr. Penguin, who is being playfully pulled by two ropes. No hurting of penguins going on here, I assure you. Playfully pull, and I don't know if you can see the grin on his face, but he's really quite enjoying this. He's on very slippery ice because I don't want to consider friction in this chapter. So he will feel a force to the right of 5 newtons and a force to the left of 3 newtons. I want to find his acceleration, the acceleration that results because of these two forces. But instead of drawing a kind of complicated figure like Mr. Penguin, we'll replace him with a dot. This is called a free body diagram because not that it's free of charge or cost, but it is free of the clutter that might be around the object of our interest. We're interested in Mr. Penguin. We're not really interested in the ropes themselves or in the ice that he's standing on. And so I reduce Mr. Penguin to a single dot, and I draw the force vectors that are going to act on him because of the rope tied to him. And we're going to move him, allow him to move along only the x-axis, left or right. I think you can probably go ahead and guess which way he's going to go because you're kind of used to tug-of-wars, pushes and pulls, and the stronger force usually wins out. So you already know that, but let's do it in a careful way to set up for homework problems that might be more demanding. Here's Newton's second law. The net force is related to the mass of the object and the acceleration, the resulting acceleration. Now I would feel better if I wrote this in vector notation with little arrows over the F and the A, but I cannot do that here in PowerPoint presentation, so you're going to have to imagine the little arrows up there. I fill in with unit vector notation the forces. 5 newtons to the right, that's in the positive direction of the x-axis, so I use a positive I. 3 newtons to the left, that's in the negative direction of the x-axis, I use negative 3I. I fill in the mass, and this is going to be a simple equation to solve. I get that Mr. Penguin's acceleration because of the pulls from the 2 ropes tied to him is 1/10 meters per second squared, and it's a positive I result, which means, yes indeed, he gets pulled off in the direction of the larger force, as we could have guessed. Here comes 2 summary points here. When you are presented with a problem with forces and you're asked to find the resulting acceleration, draw a free body diagram. There's an object of our interest. I usually call that body our friend. I draw that body, our friend, as a single dot, and I superimpose the force vectors on it, being careful to put the force vector tail on the object, on the dot itself. And next, we apply Newton's second law to the body. I usually do that axis by axis. In this example here, we only had one axis, and so we didn't have to worry about two-dimensional vectors or components or anything like that. And that's the end of our little discussion about one-dimensional application of Newton's second law.